Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Elite, the disc version developed by David Braben and Ian Bell and Aidan Bell, I hope I've got your name right, Aidan, published by Firebird. And the musician is David Dunn. So I think this is the original disc version for the Commodore 64. What I'm going to be doing in this video is hopefully extracting a nice compressed single file version of this game, and also I wanted to have a look at the line drawing routine and hopefully the model draw and maybe the planet drawing routine as well. So to be able to create a nice single file version of Elite, I need to find the game entry. So that's what I'm doing here, is that I'm setting a ranged breakpoint and seeing what the drive loading code looks like. And I know that when it's running the drive loading code, I know that hopefully the start address is going to be quite visible. In here, I'm just having a look at this protocol. It seems to be doing this loop 4 times. We can see that we've got a load X with 03, and that's at 414 in hex there, and it counts from 3 to 1 and then 0, so it does the loop 4 times, and then we've got decoding at 2 different bits. So the drive is sending 2 bits at a time, and then the Commodore 64 is decoding 2 bits for the drive load, so this means that we have a 2-bit protocol. The original version of this does not use the GMA protection scheme. I think it uses a different protection scheme on the disk, but I think the second version of Elite that was published on the disk uses the GMA protection, and one of my other previous videos I go into the GMA protection in a lot more detail and find the original author, and I'll put a link to the video in the description below. But yes, we definitely have a 2-bit protocol here. So what I really liked about this game when I was growing up was that it was a very large and expansive 3D world, and there seemed to be quite a lot of complexity behind it. But I always knew, I could pretty much tell, that it was squeezed in a relatively small amount of memory. So obviously you cannot have several different galaxies worth of planet data all expanded out in memory. It's algorithmically generated, and this is one of the great things about the game, is that being algorithmically generated was quite a feat of engineering back then, coming up with all of the generation algorithms to generate something which actually plays pretty darn well. Later on in the game you can actually go and find quests and so on and so forth. So anyway, what I'm doing now is that I'm setting a range breakpoint between 600 in hex and FFFF all the way up at the end of memory. And I'm thinking that, once the load routine that was sitting down at the beginning of the memory finishes, it's going to jump into the game. And we get to this first breakpoint here, and I'm looking through the memory, and I can see that most of the memory still has not been loaded. And I don't think it's decompressing either. I didn't see any obvious decompression going on. So what's going on here? Well, we seem to have what looks like some memory move routines, perhaps. It looks like it's setting up some memory addresses and then JSRing to 7631 and 760. Yeah, JSR to 7631, and it does that a couple of times. And 7631 seems to be doing store X load, store load, RTS, and then subtract with carry store. Yes, it seems to be doing some kind of like memory moving. So I don't think this is the main game start. What's interesting about this point here is that I can see a whole bunch of no-ops, and it seems to be no-opping out some of the original game code, which was maybe doing some kind of like setup, or maybe trying to load files or move memory somewhere, but it is doing some kind of setup. Look, it looks like it was doing some setup for DD02, DD00, which would be the VIC bank, for example. but it looks like it wasn't actually. It's actually knocked out the actual store as 2DD00. So the actual setup wasn't being done. So maybe this setup is being done somewhere else, which was also making me think that this is not really the main game entry. The tape version, if I remember correctly, the original tape version actually has a loading screen with a nice Elite logo and everything else like that. The disc version didn't seem to display anything like that. A little bit disappointing that it doesn't contain the loading screen from the tape version, but hey ho, you know what to do. It actually loads quite quickly from disc, so I guess they chose speed of loading from disc rather than displaying a loading picture. Fair enough, I guess. Anyway, yeah, this does seem to be doing some setup by, say for example, copying memory to underneath the VIC chip registers, or underneath the color RAM, for example. The kind of setup that you, or actually into the VIC chip registers itself. So the game might be trying to do some setup there before loading the other parts of the game. You can see here actually it's setting up things like screen registers and whether or not the screen is multicolour and stuff like that, which is kind of odd. Maybe this was some vestigial code hanging around which would have displayed the loading screen from the tape version, but the disc version just decided to comment all of this out with no ops, perhaps. Anyway, let's march on. I don't think there's anything too interesting in this routine here. So this init routine, I'm just going to let it do all of its memory copying, and you saw that there in the memory view. It did a whole bunch of memory copying. Now it's taking the memory that's at 600 in hex currently and then copying it all the way down into lower 0 page, right up at the start of memory. We also seem to have had these sprite frames get decompressed, so you can see the compressed sprite frames at the end of the sprite sheet, and then the monster sprites, the explosion sprites and the crosshair have now been decompressed. So actually the memory move was doing some kind of like decompression by the looks of it. Now this JSR to 400 in hex is actually, I think, getting bytes from the disk. Let's just verify that. Yeah, this is serial code, and it's getting individual bytes from the disk and then storing it in FB, FC, FD, FE. This looks like it's doing the second set of loading after doing all of that memory initialization and decompression. So look at the highlighted lines here, 502, where it does a JSR to 400 PHA, JSR 400 PHA. This does look like it is pushing the final load address, or rather the run address from the disk, onto the stack. This kind of protection method is trying to obfuscate the entry point for the game by pushing it onto the stack. It's quite a well-known trick from back in the day, but it makes it kind of like obvious to actually see. So what this will do is that eventually it will go and run some other code, and then the other code will at some point do an RTS, and then the actual real address will be pulled from the stack, and then the code will execute. If we scroll down a bit, yeah, look, right down at the bottom there's a CLI and an RTS. The CLI is going to be another kind of obfuscation where, by clearing the interrupt disable flag, basically, it enables the interrupts, and the interrupts, because they've been queued up, probably because they're on timer, the kernel will switch in and then try and run its interrupts, and it will try and obfuscate the code flow by digging around inside the kernel and executing a whole bunch of code, trying to fool whoever's trying to debug this into thinking it's just running a whole bunch of extra code, which makes it harder to actually spot when it's going to do the RTS and going to pull that start address off the stack. So here we are, those JSRs and everything are pulling a whole bunch of extra data off from the disk. I've got a ranged breakpoint that's going to hit when it's hopefully going to start executing the main code, the main game start code basically. Then right here, the two last bytes being pulled from the disk at JSR 0400 and hex there, up at the top where it does the push PHA, does the final pushes I think that last store to DD00 is probably signaling to the drive that it should revert back to its normal ROM code rather than doing a fast load or a turbo load. And then the CLI at 54F and the RTS at 550 are going to come into play at some point. But you can see it's doing a whole bunch of initialization in terms. Well, it's doing some VIC chip initialization. I think it's probably setting the bank there, actually, to be honest. And it's also clearing out a whole bunch of registers in extended zero page at 334, 434, and 534. Well, actually, that's a screen memory as well. But it's also copying a whole bunch of code from 522 to 200 in hex. So it jumps to that relocated code at 200 in hex. It does this final little extended zero page and screen memory clear, and it also sets up a couple of vectors there at 308, 309, and 326, 327. Sets up some default values 328 and 90 and NC6, and then it does a CLI, and then it does an RTS. And because the CLI comes along, it doesn't actually execute the RTS first of all. The IRQ comes along, and then once the IRQ finishes, we step out of it, and then we get the RTS, and then it's at CE27. So I'm pretty sure now that this is the game entry point code. But again, we see some no ops here, removing some of the game entry code. There we go, there's a whole bunch of memory copying and everything else, and then the game starts. So we need to save the memory for the game, and then we need to compress it into a single file to actually get that working. So a good breakpoint I think to use is actually 502 in hex from what we found just now. And 502 is when it was pulling the start address and then from the disk and then pushing it onto the stack, right? Because it contains some of that nice zero page and screen memory initialization code, I think that we want to try and keep that if we can and reuse it, because I think it's clearing out some things which the game thinks is important, right? So we'll try and keep that as far as possible. My compression tool can safely decompress the whole memory range from 200 to all the way up at the end of memory. And so I'm not too worried about saving everything from 200 to all the way up at the end of memory. That's not an issue really. But I think instead of trying to pull the last 2 bytes for the start address from the disk, what we can do is that we can push the immediate values onto the stack ourselves by editing this code. So we will just assemble a little bit of custom code over at 502. We know what the values should be. We'll push them onto the stack in the correct order, of course, because that's what the RTS wants. I'm knopping out the extra data for the instructions that we don't really need anymore, and keeping the DD00 and the D011 initialization, and also the zero page memory copying initialization, which initializes the rest of the zero page and screen memory. Okay, so I'm keeping that code. I'm just circumventing the code slightly to avoid the last 2 bytes being read from the disk, because I'm pretty sure at that point it's already done the protection check. I've just remembered actually that I need to initialize the processor port, which maps in the kernel and everything else to the values that it expects. So I need to set up that, and it wants the binary value, I think, right? So I probably want something like, well, actually I'll just enable everything how I want it. There we go, put that there. and then I will clear out the rest of the code that is unused. The code 400 onwards until about 500 or so is, the disk loading code, and I know that I don't need that anymore, so I can safely put all of my code over what was the disk loading code here. So I'm not really worried about the extra no-ops or anything like that. So anyway, I think that's a good point now to save this file, remembering of course that I want to set the bank to RAM, so I'm not saving out ROM data inadvertently. I don't want that, obviously. So let's save the whole memory range. Then let's go to my little compression tool and compress this almost the whole memory file, and then use the correct entry point address, which is at 4F8, and then let's run this new compressed file, and then let's see what we get. Okay, so initially the most obvious thing that I can see here is that the top of the screen and actually the rest of the screen colors are not quite correct. Now the top of the screen is a high resolution bitmap, so yeah, that tells me that the color memory needs to be saved and restored. At this point, let's save the color memory to the spare place in memory at the end that we saw when the game was loading, because I think that the last few pages at the top of memory are completely blank and unavailable for use. The other way of doing this is to save the color memory as a separate file and then restore the color screen memory first, and then run the decompression, which decompresses all of the other data into the RAM underneath the color memory. But in this instance, because I know pretty much that the end of memory is available for use, I'm not going to bother doing this two-stage reconstruction of the memory, what it should be in terms of color memory and then RAM underneath. I'm just going to decompress everything to RAM and then move from the unused RAM into the color memory. Let's just verify. Yes, there we go. In ICU, I can definitely see that there is default power on state for the RAM up at F000. So I think that's where we'll put the color screen memory temporarily. I'm forgetting in Vice in the monitor that actually if you have it in IO bank, it doesn't like copying from color memory to the end of RAM. So I needed to set it back to CPU before I could transfer what was in color memory to F000 in RAM. So there we go. At F000 in the top left hand graphics map text screen debugging view in ICU 64, now we have a backup of what the color screen is. So I need to copy back now from F000 to D8000. Now I'm going to do that by adding some extra code now all the way up at the start of memory, I think up at 400, because that's the drive routine which we don't need anymore. I want to look up the value for all RAM with IO, so I want to copy from the RAM underneath kernel, and I want to copy it to the IO, which includes color RAM. I wanted to put a hex value here rather than a binary value. So let's do the copy from F000 to D800 with the X index register. We start from 0, we increment until it goes to, or increment and then branch while it's not equal to 0, so it does 256 bytes worth of copying. Then what we need to do is that we need to increment the high byte address. Now we can use self-modifying code here. Because this code is going to execute only once, we don't need to worry about reinitializing the memory addresses or anything else like that. So we want the high byte, so the opcodes are stored as, opcode and then low byte, high byte. So then we're incrementing 409 in hex, and then also subsequently we need to increment 40C in hex, which increments the high byte for the color screen. Then we load the high byte for the color screen address, and then we compare it with the end of the color screen, which is 4256 byte pages upwards. So we add on 4 to D8 as we get DC, and then if it's not equal to that, we branch around and copy another bank of 256 bytes. Kind of like a standard memory copy routine, really. Then we need to... Oh yeah, that's right. Then we need to do the whole pushing the correct values onto the stack. And then we can... Oh yeah, we need to restore. I think that's what the processor port should be restored back to after we do all of the copying. Let's put it back to 3E. What the current code is telling us that it is in the register view there. So let's use 3E. Put that in the processor port register, and then we should just jump straight to 50A. So we circumvent those two get byte from drive and push accumulator calls or instructions. Setting the bank to RAM, of course, which is what we want when we're saving out the whole of memory. And the file name has changed because I've changed the start address. It's now at 400 for the extra code that I want. So let's save all of that. So let's compress that new file now. Note the file name change. Note the start address change to 400 in hex now. Then let's run that compressed file. So the compression for this tool is actually pretty good now. I'm very happy with it, and it's generating a nice small version of Elite. And let's see what we get. Let's run it, and then fingers crossed. Ooh, that looks better, doesn't it? The color memory now for the bitmap, the high resolution bitmap, sorry, at the top is all good now. The spaceship seems to spin around okay. Let's go into the game. And something's wrong, isn't it? There's no crosshairs, I don't think, right? Yeah, there's no crosshairs on the front view. So I remembered that there was some VIC initialization code that ran between the two main part loads of the game. And of course the crosshairs and some of the explosion sprites and everything are sprites. They're VIC sprites, they're not software sprites. So let's go back and reload the game as we just done. And this time, once we get to this point where it's just about to start the game code, we know that the VIC chip initialization registers have been done, so we're going to load back the single file version that we've been working on. I've been working on. And I'm going to transfer, let's just transfer all of the 256 bytes for the whole VIC chip to F400 this time. Now we need to go back to the code at 400, and before we do the jump to 50A, before we restore the processor port at 423, right? We want to keep the all RAM and IO mode switched on, but we want to restore the VIC chip registers from the backup now that we have at F400. Does anyone remember the VIC hardware registers mirroring limit without needing to look it up in the documentation. On a standard Commodore 64, I seem to remember that the VIC chip registers are mirrored. Or at least we should not be storing into any other extra VIC chip registers. Say for example for the CPU speed and stuff like that, that's in the Commodore 128. So, and that's yeah, right. So let's just copy all the way up to D02F. Have you noticed actually the copy that I took with the Vice monitor? It does seem to have. Oh, it does seem to have the memory that's being copied does seem to have a mirrored version. It does seem to have that offset. It's quite difficult to see with the data that's there, but it does seem to be doing it. Anyway, so let's add in the extra register copies. Let's go back to that save command, and then let's save the whole of memory again. Keeping the same start address, let's go back to the compression tool. Let's compress that. That's the wrong start address. Where is it? There's the correct start address, correct file name. Let's rerun now the compressed file, and then hopefully this time the color memory and the crosshairs, which are VIC hardware sprites, should be all fine. Keep fingers crossed. There they are, there's the crosshairs. Excellent. Fantastic. So I think that's a good single file version of the game now. The game seems to be working no problem at all. Let's fly around a bit quickly just to make sure everything's fine. Let's look back at the space station. Yeah, that all looks good to me. Now I've got a single file version. It's a lot quicker and simpler now to debug the rest of the game and to have a look at the model drawer and the line drawing routine. I don't need to keep on restarting the disk version and the disk load and everything like that. I could, of course, use a Vice snapshot, but to be honest, I find it a little bit easier just to run the single file version. So let's just do that. So the first thing to do is to set up a nice little ranged breakpoint for the first couple of kilobytes up at the top of the bitmap screen, high-res bitmap screen, and there we go. Once the spaceship zooms in far enough and it's covering a significant portion of the top of the screen, then we start getting to where the bitmap update is done. Now, the first thing to notice is that actually when the spaceship was small, no part of the top of the bitmap was being touched. So all of that spinning around of a small object wasn't clearing any part of the background there. So yeah, Elite uses this EOR, which is an exclusive OR operation, to toggle. It doesn't set or unset or clear pixels in the bitmap. It toggles pixels in the bitmap. So actually, if nothing is being drawn in a particular part of the bitmap, then it's not actually clearing the bitmap and then redrawing the spaceship. It's actually drawing the lines and then drawing and undrawing or toggling off just the pixels for the lines that it's just drawn. In this version of Elite, it's not patched, it's the original version, and the spaceship draw is a bit flickery because it's continuously having to do this draw and then erase function. But we can see here in this what looks like the line draw for the spaceship, or line draw generally speaking for the 3D draw. We can see that it's doing a load accumulated with 8 load accumulator with 4, load accumulator with 2 there at B63E, and a load accumulator with 1 at B661. In between these, it's doing a decrement X and it's doing a little branch, a little loop, but it's actually doing a loop. So X looks like the number of, maybe the number of X pixels. The Y index is going to be doing an index for the Y position within the bitmap. And then we have this load accumulator with 7, subtract with carry, store, load accumulator with what's in 8, subtract 1, store. So that's updating the screen coordinates. This looks like an unrolled loop to plot, or toggle rather, to flip, toggle pixels on the bitmap that are pixels shifted left or right, and then actually doing a vertical advance. So it's not every pixel that it toggles, it advances the Y position, but it's definitely seems to be toggling pixels one at a time and then doing a store, or doing a toggle with the bitmap. And there seems to be a calculation with what might be a slope or a gradient variable. So as the pixel moves across, it decides when, with the slope or the gradient, when to step down in terms of the Y coordinate, or rather step up because it's doing a decrement Y. So no wonder the line draw is so fast, is that it's doing this a nice optimized unrolled loop. And it's using extensively zero-page registers. So this routine, when I'm looking at it, it reminds me very much of a particular line drawing routine which is very useful in integer-based CPUs, which is a Bresenham line drawing routine. This Bresenham line drawing routine is a very common algorithm because it lends itself very well to being implemented in CPUs which only have integer mathematics without any kind of like multiplier or anything like that. And it's very fast because all you need to do to know when to advance your pixel position is to have a slope. The line slope dictates how often to step for every, say, Y position that you want to step. There should be plenty of, well, I know that there is plenty of reference material available on the internet. Let's see if I can find that. Hold on a second. Here we go. The Bresenham line algorithm on Wikipedia actually has a very good explanation about what it's doing. So anyway, now that the pixel plot, or rather the pixel toggle, has been found, let's see if we can find the entry point for one step further up the chain, if you like, or further up the call stack, which is where it's actually setting up the line's gradients, and before that the line's position, the start and end coordinates, to actually do the draw. It would be useful to find out where 7 and 8 zero-page registers are initialized. Scrolling up a little bit, I can see that the RTS here looks like the exit to the function. Setting up, well, BC seems to be probably the width or the height of the line. It looks like it's doing 2 different table lookups, probably depending on the gradient or the slope of the line. These are jump table lookups. These are self-modified jump tables. Look, those 2 jumps, the 2 table lookups just above the jumps are actually doing a self-modified lookup. So it's probably doing a, what pixel within the 8x8 pixel character cell for the current bitmap position on the screen, which pixel do I start toggling, and to be able to do that it needs to know where to jump into the unrolled loop for toggling the pixels. Scrolling up through the code a bit further, I can see initialization for 6B, 6C, 6D, 6E, and I think these are the slope and line length or width and height calculations. The store Y here looks like the start of the line draw because it's storing Y into 9E, and it loads Y with whatever is in 9E just before it does an RTS. So this looks like the beginning. B49D looks like the beginning of the line draw routine, and we've already got a breakpoint, I think, at the RTS at the end. The code here at the beginning definitely looks like the line slope and the line bounding box extent, or whatever you want to call it, the width and the height for the screen. Setup code, it looks like it's doing a couple of lookups into probably a couple of tables to do with calculating the slope of the line. The code just before it in the CPU history, just before it starts the line draw, look, you can see here it's doing 4 points, 2 coordinates, sorry, not 4 points, 2 what probably looks like X and Y coordinates, setting them up in 0-page registers 6B, 6D, 6B, 6C, 6D, and 6E there, and it looks like it's loading that from a table, probably a calculated line table, I'm guessing. So every iteration through this routine, look, it's drawing a line for the spaceship here in the bitmap. There you go, one line. And because it's doing an exclusive OR, the EOR instruction, it's doing the toggle, pixel toggle, it's doing the arrays as well, I'm betting. So let's keep on advancing that line. Yeah, there we go. You see, it's the line draw routine is a line arrays routine as well, as I step through each rendered or erased line. So let's go back even further. Now we've identified the entry point for the line draw, I'm pretty sure, right? Based on these empirical tests. Let's play around with the values going into the function now, what we think is the line draw function. And let's update the values 6B, 6C, 6D, and 6E. And see what happens when we manually tweak those values before the line draw routine works or runs. So let's set up some coordinates for what should be a line starting at 0 and 20, and then 40 and 60. Now we're using these values here so we can easily see at a glance what the coordinate base is of the screen, right? Because the values are all different, so then we can study what the line is being drawn as. And oh look, so the X position is the first element, or the 0 element at 6B, basically the 0, and then 0, 20. These are hex values, don't forget, so it's 0 pixels in the X and 20, which is 32 in decimal pixels down, and then 40 in hex across, and then 60 in hex down, which is 64 and 96, right, in decimal. So let's test the range to all the way to the right hand side of the screen. Let's do another line draw, but with these coordinates. So we should see something along the lines of a line going horizontally across And yeah, there we go, there's the line horizontally across. Of course, 128 pixels down is quite a ways down actually on the bitmap. 80 in hex is 128 in decimal. So actually I drew a line, or I told the routine to draw a line rather, at quite a low down y coordinate. The y coordinates advance down positively from the top of the screen, of course. Yeah, that's the usual way that these things. And there we go. The line draw with the same coordinates then erased the line, or toggled it rather, that was just drawn. So let's change the y coordinates this time. So we should get a line up near the top of the screen now. And we'll change the x coordinate so that we draw a line across the whole of the screen from 0 to FF. There we go. A line near the top of the screen now, just underneath the elite text, has been drawn. So I'm pretty sure now that we know the entry parameters for the line draw. And if we run the game now, that line should stay there, again indicating that the bitmap is actually really not cleared. Look, the spaceship rotates over or under that line because the spaceship is just, the line draw for the spaceship is just toggling pixels. There is no clear going on. It's not even a bounding box clear. So let's put a line across what we hope is roughly the middle of the bitmap, well the middle of the spaceship. Oh look, it's roughly 64 pixels down, or 40 in hex pixels down. That's probably not a surprise, is it really? Yeah, anyway, the spaceship happily toggles the pixels and there is no clearing going on in the bitmap. So to recap, I found the line draw and where the ship model drawer is, and also found the game entry to be able to create a single file. Using this information about the line draw specifically, I have a crazy idea. I want to try and extract the line draw routine as an independent routine that works outside of Elite. Back in the day, if you wanted to make a 3D game like Elite and you wanted to have a nice fast line draw routine without doing much work, you might want to try and use the code that's in Elite, right? So, first step of trying to use the code independently is to try and understand the extent of the code in the memory and what memory it touches. Now, back in the day, you would have probably had to have done a disassembly and then manually check the code execution pathways for the line routine and try and map out any tables that are in memory and so on and so forth. But in the modern world of Vice emulator and debugger, what we can do is that we can use the monitor commands to tell us the memory ranges that are touched when the line draw routine works. So we put a breakpoint at B49D. We use the mmzap command, which is memory map zap, which clears the memory map of touched values of executed memory and read and written memory. We don't have to use the memory map or mmzap button command. We can use the mmap clear button here in the Vice PDB remote monitor window, which is a GUI interface which connects to the network remote monitor on the Vice emulator. So then once we're at that breakpoint, which is at B49D, and we have a nice full memory view as well, which is quite nice and useful to use sometimes. But anyway, so once we're at there, we do a step out, and then we can do a show, which is a memmap show command. And this shows us actually all of the memory which is executed, and we can see what's being executed by the X identifier there at the end of the memory address, and we can see what has been read and what has been written with R and W. So what we have now is that now we know what memory has been read and written and executed respectively. Then we can use this information to save out some memory chunks. But first of all, we need to study this in a little bit more detail. So the 0-page registers up at the very beginning, we are not going to be worried about. Let's transfer that to a text editor so we can tidy up the list a bit better. So, probably not that interesting, because all of the reading and writing going on to the 0-page registers are, I call them 0-page registers because they're quicker to access than the main parts of memory. They're like an extended register set, if you like, on the 6502 or 6510 processor. Anyway, so these 0-page memory addresses I'm not too worried about. The code, that's not code, that's memory reading and writing. These memory addresses are writes, obviously, into the bitmap screen, which we don't care about because we know that that's the line draw. These look like reads into 9C00, which I think probably tables 9C01 to 6B, then 9D1 and 2 and 6 and B. So I think these are corresponding table reads based on the line bounding box width or height or the eventual slope lookup. So I think that we probably want, obviously we want to save these tables as a distinct block of memory. If we have a look at this, then I think we've got a whole bunch of reads at A0 and A1, all the way up to A1. Let's guess that it's going to be A1FF, for example. 9F also looks like a table for the line draw. A0. A1 looks like, these look like the low bytes for the low memory address for the bitmap data, and A1 looks like a table for high bytes for the high address of the bitmap data in memory, which starts at 4000 in hex. So I think that we'll include all of this data range as saved out data tables. So we'll get rid of all of that. Now we have a whole bunch of code being executed at this memory range. That's roughly where the entry point was, right? I think the previous memory map had some extra superfluous data or execution logs in there for particular memory locations. So let's run that again just to make sure that we have good data. I think we were starting to see execution for this part of the routine here, and we're not really interested in extracting that part of the routine there. Yeah, there we go. The extra code now that it was saying that there was something executed at A, whatever it was, right, is no longer there anymore. So I'm pretty sure that that's produced a smaller set of executable code that was running for the line draw routine. Another possibility is that because the line draw takes a significant portion of time, maybe the interrupt for where the bitmap changes from high res to multicolor came in as well, or some other interrupt. Anyway, so I don't think that we want to save out such a large range of code. I think executing the line draw routine and showing the memory map for subsequent executions for the line draw routine showed that we can save a smaller range of memory for the executable code, so we'll do that, I think. So we can save this data table memory, and we can save what we think is the code memory, and we can test it in isolation. Basically load the data files into a new instance of Vice and then run the code and then see what we get. So we'll save the range for the data tables first, and then we'll save the code memory range second. So we'll get a new instance of ICU debugger open, and we'll show the intended bitmap memory locations where it should be running the code. I think we'll fill the memory for the bitmap with 0 so that we get a whole blank bitmap. Let's remember that we need to be in the correct bank. Let's load the tables. Let's load the code. Now we need to call the code. Actually, I think to really prove a point, I'm going to fill practically the whole of memory and then load the tables and the code. So I'm filling the whole of memory with 0, basically so that it fills the memory with the break instructions, so that if there's any unintended code execution going on, then the Vice monitor will break because it's encountered the break instruction. And hopefully it will show us that there is no unintended code execution going on. So let's assemble something up at 1000 in hex, which is 4096 in decimal, which is a good area of RAM that we know is not being used. Let's set up RAM with I/O. For the line draw, and store that into the processor port. And then let's load some coordinates. Oh, first, yes, yeah, I almost forgot. Let's initialize the stack first with all of the memory for the stack. Then let's set up some coordinates into 6B, 6C, 6D, 6E. Then let's JSR to the line draw routine, which, don't forget, it toggles pixels, so it will draw and erase repeatedly the same line. In theory, let's see what we get. This is what the code looks like at 1000, so let's just run it. And there we go. So in the ICU graphics map window, in the debug window, we can see in the bitmap it is continuously drawing and erasing the pixels for that specific line. Now it's doing it so rapidly that we're getting what looks like a rolling shutter effect, which is where the memory view update refresh speed is different to is slower than obviously the pixel update speed. So what we can do now to really demonstrate the point, I think, is that we will increment the border color so that we can see exactly how long one line draw takes. Now it's quite a large line that's being drawn, and we can see that it takes a significant portion of CPU time. I think looking at this, it's able to draw maybe 2 and a bit lines of that length per frame. It's quite quick, relatively speaking, I suppose. The Commodore 64's bitmap is set up in a weird way. It's hard to update it quickly. So, to make it even more obvious that we have successfully extracted the line draw routine, let's increment one of the coordinates, and then let's go, and there we go. Now we're incrementing the start point, the first coordinate for the line. The line draw routine can now show this nice looking effect where we continuously draw and erase lines of different gradients with different start positions, basically. The bottom of the screen is also updating its line. So the line draw routine seems to have a break in the bitmap coordinate base, which is what you would kind of normally expect, right? Because the main game doesn't render ship 3D models over the bottom part of the bitmap data. So the table doesn't extend to the full height of the bitmap, I guess. But the coordinates, I was incrementing, right, the y coordinate, so it was stepping over that boundary. So don't worry about the bottom portion of the bitmap, just worry about the top portion of the bitmap. So there we go, updating all 4 of the values, so both coordinates basically, shows this rather nice little twisty, turny line effect with that kind of like distinctive EOR or XOR pixel pattern for lines which are very close together and rotating or moving around in very small steps. And you get that lovely, very distinctive effect. And now we can see how fast the elite line draw routine is, and we can see now that we've successfully extracted the elite's line draw routine, so that if we wanted to, we could build a game around this, or a demo, or whatever, more precisely disassemble the line draw routine and then reassemble it at a different point in memory. Anyway, so I think I'll leave the video here. It's going on long enough already. And so if you like these kind of technical deep dive sessions into old Commodore 64 retro games and the memories that I have associated with them, then please do consider liking or subscribing to this channel, and there are some buttons down below specifically for that purpose. And I always like to receive comments from people and feedback. So thank you very much for watching. Take care, have a great day, or afternoon, or night, wherever you are.